In this lecture segment, we're going to look at a somewhat more elaborate program, prog2.s. This program performs a loop to add up the numbers from 1 to 5 and then returns the result as its exit code. Register 0, our 0 over here, will hold the sum, and R1 will hold the value to add into the sum. So the move instructions on lines 4 and 5 here initialize those registers to 0 and to 1 respectively. Now let's skip lines 7 and through 9 here for the moment and look at lines 11 and 12. These are add instructions. They add their two rightmost operands, like R0 and R1 here, and then put the result into the left operand. As the comments indicate, they're essentially assignment statements, like R0 equals R0 plus R1. Now, like move, they're limited in their operands. The target and the first of the two right-hand operands must be registers. The final operand may be either a register or a constant, or several other possibilities that we'll look at later. Clearly, we're using a constant in the second one, which increases R1 by 1. Now, the most interesting new feature of prog2.s is actually the loop. In order to add the values 1 through 5 into R0, the program must repeat the lines 11 through 12 over and over, adding increasingly higher values of R1 into R0 until R1 exceeds 5. Assembly language includes no while, for, or other loop keywords. It offers only branch instructions, which jump from one point in the code to another. For instance, the branch instruction B down here on line 14 makes the program jump back to line 8, which is labeled as loop top. It thus repeats lines 8 through 12 over and over again. But those lines should only repeat as long as R1 is less than 6, since we're adding just the values 1 through 5. And lines 8 through 9 take care of this. Line 8 is a compare instruction in the opcode CMP. It compares two operand values, in this case R1 and 6. And that's all it does. Any action based on the result of the comparison requires a subsequent instruction. The CPU remembers the results of a comp until the next comp or until some other instructions are executed. We'll have more on that later. Line 9's BGE instruction is a conditional branch. It jumps the program to its target location, all done, only if the result of the prior comp was greater than or equal to. In other words, if R1's value was greater than or equal to 6. Line 9 is thus deciding when to exit the loop. When R1 reaches 6, line 9 jumps past line 14 down to the bottom so that the program can finish and exit. The final two lines set up and perform the SW1 instruction as in prog1. Note that the sum is already in R1 as the exit code. Now, to be sure that's clear, let's follow the first several loop iterations. We start with R0 and R1 at their initial values of 0 and 1. The comp and BGE instruction pair does not jump, and we proceed to the two add instructions, adding R1 into R0 and incrementing R1. We then branch back to loop top to do another loop iteration. And again, the CMP BGE pair does not jump, and the subsequent add instructions increase R0 to 3 now, adding R1 into it, and then R1 is incremented to 3 as well. And loop iterations continue like this until R1 reaches 6, at which point R0 will be 15. At this point, the CMP BGE pair does jump to all done, and the program exits with code 15. I'll compile or assemble and run the program here so we can see the final exit code of 15 confirming that it works. So I have prg2.s, and I'll do an asprg2.s ld run PRG2 and do the echo $question, and there's our 15. So a few in-lecture questions here. There are other forms of conditional branch than just BGE, testing for things other than greater than or equal. Look these up in the course resources and name the opcodes for various different relational branch tests. If you found the right stuff, you should have come up with things like BLT, BLE, BGT, BEQ, BNE for less than, less equal to, greater than, equal to, not equal to, respectively. So we can test any of the various comparisons we might want. Now, lines 8, 9, and 14 are the way that you do a while loop in assembly. You start with a test to see if the loop should end. Up here, the BGE. And if that's true, you branch past the end of the loop. After that, you put the loop body. And then an unconditional branch after that to go back up and repeat the test. In the same way, any higher language control structure, for instance an if-else or a do-while or a for, can be imitated with the right pattern of compare, branch, and branch XX instructions where XX is some test like GE. So, with that in mind, let's do some revisions on prog2.s and try a little bit more assembly. Revise prog2.s so that the loop, first of all, decrements R1 from 5 down to 1. Now, you'll need to change 4 instructions, and you'll need to research and use a new opcode sub, which does subtraction instead of addition. So, what you should have come up with after some thought there is that at the start we're going to have to modify R1 to be set to 5, right? And then when we compare, we're looking for R1 to be above 0. We want to stop when it becomes equal to 0. And so we'll compare against 0 here. And the BGE now needs to be either a BEQ, which would work once R1 becomes equal to 0, or perhaps a little more complete, a BLE. In any event, that branches down to all done. And then finally, this add here needs to become a sub instead. And that would do the loop in decrementing form. Now, question 3. Write the assembly that would perform an if statement like the one in the notes, in which I repeated here in the diagram. So, as a brief hint, if you came up with an answer that comprised 3 assembly instructions, a compare, a branch, and a move, and a label, then you're on the right track. If you didn't, maybe think a little more before looking at the answer. So, at least one reasonable answer would be to compare R0 and R1, and then if R0 is less than or equal to R1, the false case, right, do a BLE then to a label we might call after. That'll route around the body of the if statement. The body itself is a move R0, R1, and then we will need that after label to be before whatever code follows. And again, it's sort of a negative test. We ask if the if case is false, if R1 or R0 is less than or equal to, and we branch around in that case. Otherwise, we fall through and do the if. The idea of jumping from point to point in an assembly program implies some means of tracking where we are, what the current assembly instruction is. The current assembly instruction is at some location in memory, so a 32-bit value will tell the processor what instruction is being executed and what is next. Every CPU has a register holding this location, generally termed the program counter, or PC. In an ARM process, R15 is the PC. R15 cannot be used for mathematical operations. It always stores the current instruction location, and from henceforth we'll label R15 as PC. And a question regarding that, a B instruction can use a numerical address instead of a label. So for instance, we could write B pound 160 to jump to memory address 160. Write a move instruction that does exactly the same thing. The answer is, given the role of R15 as the PC, a move R15 pound 160 would do the same thing. And in fact, a move PC will also work. You can use either one to describe R15 in assembly. Note, by the way, the larger jump address wouldn't work because move can only use small constants. And while we're talking about registers, an ARM CPU remembers the outcome of a CMP instruction by storing information on the result of the comparison in a register we haven't discussed yet. This is the Program Status Register, or PSR. We'll discuss it in more detail later, but briefly, the PSR stores a number of bits of information about the program, including the outcome of a CMP. A CMP instruction actually subtracts its second operand from the first, but doesn't store the difference. The PSR, however, does devote several of its bits to record whether the result is 0, negative, and several other conditions that we'll discuss in an upcoming segment. These one-bit flags in the PSR are called condition codes. So for instance, the instruction CMP R1 pound 6 actually computes R1 minus 6, but it doesn't store the difference. The condition codes in the PSR, however, remember whether the result was 0 or negative, and then BGE, all done, checks the PSR condition codes to see if the result was either 0 or not negative. Either case would imply that R1 is greater than or equal to 6, and the BGE branches if so. The PSR only stores information about one instruction. A new CMP wipes out any results from prior CMPs. The PSR can also store information about other instructions, an add or a subtract for instance, but only when they're specially marked to do so. The PSR always stores information about a CMP. Any instruction can check the PSR condition codes and execute only if they satisfy some criteria. And later we'll see cases where non-branch instructions do this. But by far the most common case is for branch instructions to execute conditionally based on condition codes in the PSR, resulting usually from a prior CMP instruction.